Hi everybody. So today we're going to talk about drill bits. Drill bits are a very powerful tool in the machine shop. If you're like me, you have a bunch of them, or you might just have a handful of them. And I'm going to teach you a little bit about the drill bit today, a little bit about what it's made of, different styles of drill bits. And then in a subsequent video, we're going to talk about how we sharpen those drill bits, because you probably have a handful that are dull. You might think that they're useless now, but actually you can sharpen them up pretty quickly and continue to use them. And you don't have to have anything really special other than a bench grinder. So let's talk a little bit about the drill bit. So we are going to be talking about a specific type of drill bit. So you might have had experience with other types of drill bits. They come in all different shapes and sizes. We have auger bits, we have masonry bits, paddle bits, unibits, chamfering bits, all different styles of bits out there. But the one that we're going to talk about today is called the jobber drill bit. And the jobber drill bit is kind of our baseline twist drill bit. You buy these all the time at Home Depot or Lowe's, but they're a pretty powerful tool in the workshop because they're one of the best tools with the highest what we call material removal rate, meaning that we can evacuate and cut through material pretty much the fastest out of any process using a drill bit. So they're super powerful when we're machining to be able to use these drill bits to step up bore diameters and that sort of thing and remove a lot of material really quickly, which would take a lot more time if we were using like a boring process on the lathe or something like that. So we're going to look at the jobber drill bit. The jobber drill bit, well, drill bits in general, I should say, date back thousands of years. So there used to be just a paddle drill bit spun back and forth by a hand drill or a bow drill or something like that, and it would just slowly eat away at the material, cutting off little tiny flakes, here and there, and take a long time to get through that material. They weren't really good at removing material. They weren't very good at evacuating material. So in 1863, Stephen A. Morris developed the twist drill, which is the jobber drill, the drill that we know of today. Side note on that one, Stephen Morris was also the guy that gave us the Morris taper. We've used the Morris taper on the lathe. That's what goes into the tailstock. They're widely used in machining, the Morris tapers are. So this guy has very benefited the machining world back in the mid 1800s. So let's look a little bit about the anatomy of a twist drill. So the shank portion is this portion up top here. This is the portion that we hold on to. Now, just like in end mills and everything else, we can have a lot of different lengths and obviously diameters. We can have something, there's a silver and Deming drill bit, which has what's called a reduced shank. So the shanks are a 1/2 inch, but the flutes and the cutting edge up top there are all a lot larger, 3/4 inch, that sort of thing. Something that we couldn't fit in our chuck. So if we had a 1-inch drill bit, a 1-inch shank wouldn't fit into our chuck, but a 1/2 inch one would, so we step it down to a 1/2 inch. But shanks come in all different lengths, just like flute lengths do. Same thing as with an end mill. So the shank's what we hold on to. Just like with an end mill, we're never going to hold on to any of the cutting area. But I'm going to talk to you a little bit about the cutting area, which is not really a cutting area up here, but the flutes. So the flutes are the actual recess portion of the drill bit right in here. The only purpose of the flute is to evacuate the chips out. There's no cutting that happens along these side surfaces right here. The landing or the land up here, this is actually, the land is there's two parts to the land. There's this section right here, and then there's also this section. We look at this, there's this little tiny portion, and this is a land right here. And this is the only portion that contacts the side of the hole when we're drilling. Nothing else contacts, and none of this does any sort of cutting. The only reason for this land right here is just to keep the drill bit square in the hole, true in the hole, so that we drill a straighter hole. And then again, the flutes are just what remove the material out of there. So if we're looking at it from the front side here, we have, this is the void of the flute there. The cutting action only happens, this is the only area that the cutting action happens, is right here and right here. These are called the cutting edges or the cutting lips. That's the most important part of the drill. That's what makes or breaks the drill. So we're going to be talking about later on about how to sharpen those, and we're going to be focusing very heavily on that. On the back side of this here, there's a relief. So kind of like if you remember when we were grinding our single point cutting tools, we have to have a little bit of relief. Otherwise, the drill bit or the cutting tool will drag after the cutting edge. So you'll notice here that, and it's kind of hard to see in this image. I'll show you an image here in a second. This actually fades away here. So it's not perfectly in line with the cutting edge. And then we have this part right here. This is called the chisel edge, which is this center section right here. That's going to be important. I'll tell you about that in the next slide as well. And then this section right here, this is called the web thickness. And what the web thickness is the only section of solid material that runs through the length of the cutting area or the flutes. So imagine that as we've spiraled around with these flutes and we've cut these flutes into it, this is the material that's remaining. So this is really the only thickness of drill bit that is solid in this whole setup. So that's why, you know, when we start getting down to smaller drill bits, you can imagine that this web thickness here is really small. I mean, very, very inconsequential. So that's why they break so easy, and we have to be careful with them. So let's look here a little bit at a couple different cutting edges and chisel points here. So there's two different styles that we have. We talked about the fact that the cutting lips, which in this image right here, these are the cutting lips right there. The cutting lips are the only part that does the cutting. This one right here is called a split point, and this is a standard point right here. So a split point, you can see that there's a secondary grind, and actually this on the split point, this part does cutting as well. And the reason that that's important, and the reason that we do this with drill bits, not just have a standard edge right here, is you can see that this chisel point is a lot bigger than this chisel point right here. Pretty small, pretty big. And the reason that that's important is that the chisel points don't cut any material. The chisel points actually just smash material and mush it out of the way until these cutting lips can get a hold of it and cut the actual material. So we want that web thickness, or excuse me, that chisel point as small as possible so that we don't have to mash through material to get our drill bit through. Now, the downside to this split point here is that it's a lot harder for us to sharpen. So sharpening a standard point like this is pretty easy, but a split point is a little bit more difficult. Actually, I don't want to say impossible on you know, just a bench grinder. It is doable, but it just takes a little bit more finagling to do. Also, there's a couple different angles that we need to concern ourselves with. And that is the angle, the included angle of the drill bit. So if you look at the drill bit from the side, it comes to a point. Well, there's two main angles that we're going to be talking about that are used in machining. And those angles are 118 and 135 degrees. So 118 degrees is our kind of our general purpose angle. It's good for the majority of materials, good for, you know, aluminums and wood and some mild steel and that sort of thing. 135 degrees, this is our hard material. It's less steep of an angle, has a lot more rigidity in the tip. So that's going to be one that we use on a harder material. 90% of what you're going to buy off the shelf is going to be this 118 degree. 135 degrees, you have to look for those, you know, at tooling supplies and that sort of thing. One other, you know, mention on the chisel point not cutting. This is the reason that we do pilot drills. So when we're drilling a larger diameter hole, we don't just start off with that large diameter drill bit. We do what we call a pilot hole, and a pilot hole is a smaller diameter pilot hole. So how big does that pilot hole need to be? And the answer is it needs to be at least bigger than the chisel point, because the whole point of doing a pilot hole is not necessarily to get a straight hole. There's actually a lot more rigidity in this bigger hole, or in this bigger diameter, that's going to make it not walk as much as other drill bits might. But the whole point is that we don't want to fight pushing through that material with that chisel point. So if we pre-drill it, pilot drill it, and we drill larger than this chisel point, because the drill on our chisel point, or a drill on our pilot drill, is going to be a lot smaller. So we're not having to mush a lot of material out of the way with that guy. then this one's going to pass through a lot easier. So pilot drill, we're using larger diameters, just larger than the chisel point, and then you know, different angles that we talked about. Again, 118 degrees, what we're dealing with there. The last thing I want to talk to you about is helix angles. So helix angles, this might not be something that you ever even heard of before, but that's the angle at which these spirals or these flutes are formed into the drill bit. And we can buy those with different helix angles. So a standard helix is about 30 degrees. And so here's a standard helix right here, and you can see how it winds up here at a kind of a consistent rate, obviously. We can actually get the drill bits with varying helixes as well. For different material removals and that sort of thing. So this is, again, kind of a general purpose helix, 30 degrees. It's removing material up this helix, works pretty well for that, but it's not too steep that material falls back down in here. Now, this is what we call a slow helix, and a slow helix is less of a helix angle, and you can see that there would be less amount of helixes over the duration of the flute length. So we use these in harder materials. Slow helix are used for hard materials for a couple different reasons. One is when we start increasing the helix angle, obviously you can see that we're actually removing more material out of that. Removing material out of the drill bit means a weaker or a less rigid drill bit. So the more rigid, the less it's, the harder we can push it, the less it's going to flex, that sort of thing. But it's not very good at material removal. We're not going to be pulling those chips up and out of the flute as easy because they're just going to fall back down the helix. Another reason that we do this, and we don't use something like this, a quick helix, which you can see this has, you know, a lot more flute ground into it. Quick helixes are used for very soft material, is something called the drill running ahead of you. So what do I mean by that is if you look at this, this looks pretty reminiscent on this 40-degree quick helix of a screw, right? And so our cutting lips are happening here at the end, and they're grabbing the material, and in essence, they're trying to pull the drill bit in. Well, if it's pulling the drill bit in, this is going to act somewhat like a screw thread, and it's going to try to draw the drill bit in faster than we want it to draw in. So a slower helix is going to allow us to use pressure from the cutting application. So either, you know, with the quill or whatever, to apply the pressure and drive it at the feed rate that we want to drive it at, rather than having that drill bit trying to pull through the material. Now, that being said, quick helixes obviously work really well on soft material where we can move pretty quick and we want to go through them pretty quick. And you can imagine the conveyor system that happens up here, drawing those chips up and out of the hole. And, you know, when we pull out the drill bit, if we have a quick helix like this, those chips are going to stay in the drill bit and we can kind of, you know, pull them out of the hole. So again, slower helix, more rigid, harder materials, quicker helixes, softer materials, and for moving at a quick speed. So that's a quick down low on our twist drill bit. We'll talk more about the different angles and such which we grind our points in, and how we go about sharpening drill bits. It's actually a relatively simple process, takes a little bit of practice, but it's not too difficult to do. So with that, I'm going to leave you for today, and we will join again when we start talking about sharpening drill bits. So have a great day.